All right. Let's just jump right into new stuff so I can get to where you need to be to do more problems. And then in the last 10 minutes of class, the quiz is short. There are no problems on it. It's just asking questions about lecture. But in the last 10 minutes, we'll do the quiz. Yes. Yes. Yeah. Microns is micrometers. So a micron is 1 × 10⁻⁶ meters. But as I told Naomi, that is a perfect question to ask Google. If you're... Yeah, not during the test so much. Yeah. Google has lots of good information at its fingertips. Oh, well, they're going to be small, really small. You know, normally, like the biggest strains you would ever see in a realistic setting is 1 × 10⁻⁴. You know, 0.000 whatever. Well, it depends. Different materials have different. So that's not really like, you can't count on that. To figure out when a material is going to break, stress is more useful than strain. But yeah, no material with a linear relationship between stress and strain can have a strain of over 1 to the -4 without permanent damage.
You know, it's funny too, you mentioned that, because that is consistent about, one time ago I worked at a company that did curtain wall. And we were working on different materials. All of them had,
oh yeah,
decimal tolerances.
Yeah, right, yep. So you should listen to me. Okay, so let me start with an example. Let's say we start out with a cube where all the side lengths are 1 centimeter or 0.01 meters. And looking at it in this coordinate system, after deformation, let's say that this picture changes to this, where this height is 0.015 meters. The width is 0.007 meters. And if you measure this angle, it comes out to 1.3 radians. And all of the lengths that you can't see, the out of plane lengths and angles, they stay unchanged. So everything you can't see stays the same. What are the strains? So for the strain along the x-axis, epsilon xx, we have the final length along the x-axis. In this case, that's 0.007 minus the initial, 0.01, divided by the initial. It's meters in the numerator, meters in the denominator. And so you get a value of negative 0.3. Then for epsilon yy, the final length along the y-axis is 0.015. The initial is 0.01 divided by the initial, 0.01. And you get positive 0.5. And then the last non-zero strain is the XY shear strain. Yep. Okay, I was going to get to that in a second. Yeah, let me just finish this and then I'll talk about that. The last one is the shear strain between the X and Y faces. Is that 1.3 radians the angle that we want to calculate this, or do we want the angle across from it? Well, yeah, you're right about the diagonal. I was thinking we either want this one or this one. We want those two, what's supplementary angles? Well, we want the ones between the positive X and the positive. So if X was an alien, what face would be a human astronaut?
Right.
Yeah, right. And if Y was an alien, what face would be a human astronaut? How? Okay, so we want the angle between this and this. Okay. So that is the angle we want. And so the XY shear strain is pi over 2 minus 1.3. And that gives 0.271. These are all taken to be realistic. It's just an example of how to do these calculations. Okay, so now the last question is, we didn't see this when we were calculating normal strains when the angles didn't change. But now there's sort of this weird thing that happens when the angles change. How do we measure the deformed length along in this case, the y-axis is the one that looks a little weird. Are we sure we want to measure the height, or do we want to measure the length of that hypotenuse? You know, you could do the trigonometry of it all and figure out what that length is. And the answer is, for us, since this whole approach only works for small strains, small deformations, those two approach each other as that angle gets small. If you have an angle change of 1 times 10 to the minus 4 or less radians, this is this for all practical purposes. And so that's not an issue that you have to worry about. Okay, it's something we can gloss over because of the small angle changes. Yep.
So it was 1.3 radian. The origin. Like when we choose the origin.
The origin never comes into these calculations.
That's why it's XY. It's the angle. Like it's
Okay.
This way, so it's kind of like.
So the way to think about the positive X and positive Y faces is think like, like an alien. You know the movie Alien?
Yeah.
The alien needs to start inside your stomach, right? That's what it needs. And then from there, it needs to get to the sunlight.
Oh,
So
okay.
take this X-axis, start in the stomach, and then follow the X-axis to the sunlight. And whichever face you hit, that's the positive X face.
So
yep.
This way, this direction.
Right.
It's not from the end. It's from it's going through the.
Right. That's right.
Yeah.
It's always going from the stomach to the sunlight in the direction of that axis.
So where do you put the X and Y?
Yeah, you can think of putting them in the middle.
In the middle.
Yeah, you can think of it
In
that
the
way.
middle, okay, I see. Yeah, and this one is what is positive.
Yes.
Thank you.
Yes. So that was, yes, that was the idea, is that if I drew it if I drew it out of plane, all the angles would be 90 degrees still. And so these are the three non-zero values. And then we also have epsilon ZZ is equal to gamma XZ is equal to gamma YZ. These are all zero. And what are the units for strain?
No, you.
Right, no units. Any questions, other questions about that example?
How about if it's shows the same figure, just like this any sum that is the same amount.
Yeah.
But giving different coordinates, like instead x y, giving like y z.
Yeah.
Does that also change the way?
Yeah, it changes which faces you care about. And I did an example like that last time, so you might want to just glance back at that. Maybe it'd make more sense the second time now. You know. Yep. All right. So, how do we organize the strains? With stresses, we talked about the stress tensor. So we have these 6 independent stress values that are organized into this matrix. The strain is not a tensor. There are some kinds of strains that are, but this one doesn't have the properties of a tensor. And so there's no, the usefulness of writing the stress as a matrix is that it has the properties of a tensor. Strain, we're not going to write as a matrix because it doesn't have those properties. And so we're going to organize it into the Voigt form, the Voigt strain. Yeah, and that's just the name of a way, you know, these are 6 values. You could organize them however you want. You could think of your own way and then, you know, name it after yourself. But someone named Voigt did it this way, and that's what we're going to do, you know. So the Voigt strain, and I'm going to write it as epsilon sub v, is a column matrix. It goes like this: XX, YY, ZZ. So far, everything is just like you would expect. And then obviously the next 3 would be gamma XY, then gamma XZ, then gamma YZ, except it's not. I don't know, maybe there's a good reason for that. I'm not sure what it is. But the order of the shear strains is the exact opposite of what you would expect. So the next one is gamma IZ, then gamma XZ, and then gamma XY. I don't know how it came up that way, but that's just how it is. Yep, so all 6 strain values are just entered in this order. These are opposite what you would guess, what you would expect. We are also going to use the Voigt form of the stress for some calculations. So we'll sometimes also use the Voigt stress. And the Voigt stress is in exactly the same order as the Voigt strain, so I'll call it sigma sub v. And it's equal to sigma xx, sigma yy, sigma zz, And then there's two ways to write the shear stresses. You see them both ways. So I'll do it first as sigma yz, sigma xz, sigma xy. You also sometimes see it written where those shear stresses are all the Greek letter tau. So xx, yy, zz, tau yz, tau xz, tau xy.
So basically, why is it like organized this way? What happened to the other components? Are they not in the
The other components, because of symmetry, are redundant. Okay, remember, if you have a symmetric 3x3 matrix, only 6 of those 9 values are independent of each other. So this is all of the 6 independent values. That's all the information we need. Okay. And the benefit, the reason we'll use this Voigt form is that for linear elastic materials, or in other words, for materials with a linear relationship between stress and strain, that's right, exactly. So that's this whole class deals with materials of this type. The Voigt strain is equal to a matrix. This is a 6x6 matrix called the compliance times the Voigt stress. And also, equivalently, the Voigt stress, so sigma xx, sigma yy, sigma zz, tau yz, tau xz, tau xy is equal to a 6x6 matrix called the stiffness matrix. Times the Voigt strain. Okay, and is there a relationship between the stiffness matrix and the compliance matrix? Yeah, and if you think of it as what matrix would you have to multiply to the left of both sides to isolate the opposite column vector? These are inverses of each other. So where the compliance matrix is the inverse of the stiffness matrix, and vice versa.
Remember, there's same relationship between equal compliance matrix and like how is defined as the voice string. Like,
Yep.
um,
Yep. So that stiffness matrix we're going to use is always multiplied by the Voigt. Yeah. One thing. So here's something that you should, you can use to make sense out of the answers you get. So why are they called the compliance matrix and the stiffness matrix? You can think of this as a measure of how easy it is to stretch, deform a material. The values here are going to be big if the material is really easy to deform. It has a high compliance. Okay. This one is like the inverse of that. If you have a material that's really stiff, really hard to deform, then you're going to have big values here. Our strains in realistic situations are going to be tiny, right? Smaller than 1 times 10 to the minus 4. Our stresses are going to be big, bigger than 1 times 10 to the 6th. So what does that say about the value of these compliance elements? Are they huge or tiny? They're tiny, yeah. And for engineering materials, like, do you ever think of you get hit in the head with like a piece of steel or whatever, and you're like, ooh, that was compliant, Like, no. So this is going to be super small. The stiffness, that means that the stiffness elements are going to be really big. So these are going to be times 10 to the minus something. This is going to be times 10 to the plus 9, something like that. Yep. Mm-hmm. The tau? What's it doing there? It means the exact same thing as the sigma. Those are just 2 different notations people use sometimes. So if you see a tau, it's just referring to a shear stress, just the same as if you see a sigma with non-matching subscripts. They both just mean shear stress. Just 2 different ways you see it written. Sigma is stress. People always use sigma for normal stresses. Sometimes they use taus for shear stresses, and sometimes they use sigmas for shear stresses. So sometimes they make these all sigmas, sometimes they break them up like this. And for shear strains, with the type of strain that we're using, people always use epsilon for the normals and always use gammas for the shears. Yeah. No, I don't have any preference. You should be ready you should know what both of those mean, Yeah. Now, next question is, so this is the first glimpse we've seen suggesting that if we know how to characterize a material with this stiffness matrix or this compliance matrix, then if we know the strain, if we measure the strain, we can calculate the stress. And if we know the stress, we can calculate the strain. That's the same thing we know with springs. Once you measure the spring constant, if you see that the spring is compressed a centimeter, you can calculate the force. Okay, that's a lot of calculating power we have. The problem we still have is, in order to represent a material, we need to find these 36 elements of the stiffness or the compliance matrix. So do we really have to do 36 measurements to determine these matrices for a given material. A lot of them are going to be zeros. Yep. So yeah, you're right. A big chunk are going to be zeros, and then the determine these. So the answer is no, we don't, and that's a good thing because, you know, if you had to figure out a way to stretch a material and then compress it and then shear it at a certain angle without compressing it and then subject it to pressure, and like 36 of these tests to measure these 36 values would be a real pain. But if a material is isotropic, who remembers what isotropic means? Same behavior in every different direction. That's right. For isotropic materials, all 36 values are derived from just two parameters. And so in order to fill this 6x6 matrix, you don't need to do 36 tests, you just need to do 2. And then you can fill it all in with the formulas. So that's a big deal. The parameters are called, so the two parameters are Young's modulus sometimes that's just called the stiffness. Also known as, or what? The stiffness. AKA the modulus of elasticity. And it's denoted by a capital E, and it has SI units of pascals. And this is just a measure of how hard it is to stretch a material. So steel has a really big modulus of elasticity. Silly putty has a really small one. And then the second is Poisson's ratio. It doesn't have any other nicknames. That's denoted by the Greek letter nu. It's unitless. And it measures when you stretch a material in one dimension, how much do the sides contract in? Okay, so if you take most materials, if you push on them, the sides bulge out. And if you pull on them, the sides suck in. And so it's a measure of that out of plane correction that's made.
Was that like a problem we did with the cone that was applied, although it didn't change the.
No, it's not like that. Because this has to do with strains. That was just a stress-related thing. This has to do with deformations. You can measure Poisson's ratio without knowing anything about forces and just measuring the deformations in the two along the two axes. So when you stretch material on one axis, how much does the material contract? On your axes. So how do you calculate these? How are these measured? And you take those measurements in a tensile test. And so the idea of a tensile test is you take some sample piece of material and you clamp the two ends. Let's say that, let's call the x-axis along the long axis of this sample. And you apply forces here. And you measure the force applied you measure change in length along the x-axis. So that's the one that you would expect that you would want to measure. You're applying this force to pull it apart. How much is it stretching? And then you need to measure along one of the other two axes. I'm going to do it about measure along the y-axis, but you can do it along the z-axis just as well. You get the same answers. So I'll say y-axis, but it could also be the z-axis. From these measurements, you can calculate stresses and strains, normal stresses and strains. And the Young's modulus is the stress along the x-axis, the normal stress along the x-axis, divided by the normal strain along the x-axis. And Poisson's ratio is equal to the negative strain along the off axis, so I'll call that epsilon YY, divided by the normal strain along the loading axis. It's just because you get the, it's just so that this is always going to be a positive number. Because like if you stretch it, this is going to be positive. This is going to contract, so it's going to be negative, so that negative there switches it. Poisson's ratio values always lie between 0 and 0.5, where 0.5 represents a material that's volume stays the same as it's deformed. So nu equals 0.5 means the material is, it's called incompressible. And that means that the volume stays constant. Most metals have a Poisson's ratio somewhere pretty close to 0.3. So if you ever don't know a Poisson's ratio and you're dealing with metals, just use 0.3. You get pretty good answers. Okay. Let me do a quick example. So let's say that we have a rectangular solid. And before the tensile test happens, before deformation, this length is 2 centimeters. This length is 1 centimeter. And the height is 10 centimeters, 0.1 meters. I'll use a coordinate system with X that way, Y that way, and that means Z has to be that way. And let's say that an external load is applied, it's put into tension, and the value of that load is 5,000 newtons. Under this load, we measure that the length changes from 0.1 meters to 0.1, how many zeros do I have? 1, 3 zeros and then a 3. So that's L. This is the width. The width changes to 0.009992. And we want to calculate Young's modulus and Poisson's ratio. 5,000 newtons. And actually, I'm not going to do this right now. Sorry, I'll come back to this on Friday. Let me just give you the form of that matrix, and then you can start working on some problems, and then we can do the quiz. It'll be fast. Okay, to be continued. Once you know those values, compliance matrix, the one we're going to use more often, has this form. 1 over E, negative nu over E, negative nu over E, and then 3 zeros. Then that 1 over E just keeps moving across, one by one across these normal elements. So we have negative nu over E, 1 over E, negative nu over E, and then 3 zeros. And then negative nu over E, negative nu over E, 1 over E, 3 zeros. And then the fourth row is 3 zeros. And then the fourth element is 2 times the quantity 1 plus nu over E. And then 2 more zeros. Then 3 zeros, and then this element just one by one moves across the last 3 elements. So now 0, 2 times the quantity 1 plus nu over E, 0, and then 0, 0, 0, 0, 0, 2 times the quantity 1 plus nu over E. And so once you come up with the values for Young's modulus and Poisson's ratio, you can fill out this matrix for whatever material you're doing. And then if you know the stress values at a point, you can multiply this matrix times the Voigt stress to get the strain.